Here we have a model of a longitudal wave. Longitudal waves generally carry sound, among other things. Unlike a transverse wave, a longitudal wave does not move in an up and down motion, but rather in a sideways motion. They move by particles hitting each other, so as one particle moves, it hits the next, which hits the next, which hits the next. Where the particles hit is called a compression. The wavelength of a longitudal wave is measured from the distance from between compressions. So in this model here, the wavelength will be measured from here, where this marble hits this marble, to here, where this marble hits this marble. The amplitude of these longitudal waves is sort of measured between how crowded the compressions are, so how many particles are involved in each one. In this model here, there's only going to be one particle, which is a marble, in each compression, so it's going to have quite a low amplitude. Now it's time to demonstrate this model. The particles are being represented by marbles. Now these are what hits each other and causes the wave to move. The tape measure here is just acting as a track for the marbles to stop them going everywhere, but it also allows us to make sure that the marbles are reasonably evenly spaced, which at the moment they aren't, but that's alright, because I think it's probably reasonably safe to say that in the world, the particles aren't always going to be the same distance apart, which we'll talk about a bit later. The vibration for this wave, because that's how waves are made, is going to come from my hand, which is going to push this marble into this marble, which will go into this marble, which will go into this marble, which will go into this marble. As mentioned earlier, particles are not always the same distance apart. For example, in this solid, they are much closer together than they are in the air, which is hanging around here. For this reason, the wave will travel much faster through a solid or even a liquid than it will through gas, on the account of the fact that the particles don't have to travel so far to hit each other. This can be represented on the model here by putting the marbles, or the particles, closer together. So let's have a look and see how much faster it is. The same thing can be represented for other states of matter, simply by moving the marbles closer and further apart. Here we have a very simple model of a transverse wave. Transverse waves, unlike longitudinal waves, work through an up and down motion, which is created by an up and down vibration at one end. This model is created with a bit of rope, which at one end is tied to a chair to fix it, and at the other end is just somebody vibrating it up and down, and the waves can be seen through the rope. The wave moving through a heavy material can be represented by using a heavier rope. Unfortunately, I don't have one, so I couldn't do it. We could also use a lighter rope to represent a lighter material, but again, don't have one. With a heavier material, it's going to require more force to create the wave. With a lighter one, it'll require less force. This is going to greatly change the amplitude of the wave, and can quite potentially change the speed of the wave due to a decrease or increase, depending on if it's heavy or light, in the frequency of the wave. We'll talk about amplitude and frequency a bit later. Changing the material that the wave is moving through can also affect the wavelength, and in turn this will greatly affect the speed of the wave, as the speed is equal to the frequency times the wavelength. To get a better idea of how a transverse wave works, I'm going to draw a diagram of one. So, here we have our wave, Now that's not perfect at all, but we can see our wave, and I mean, if you saw the rope wave, it certainly was not perfect. So, our different parts of the wave. The first one would be wavelength, which is here. So that's from peak to peak. There is your peak, and there's a peak, and there's a peak. But it can also be measured from trough to trough, that's trough, it's just the bottom bit. So that is wavelength. And the other part of, well, a wave is the amplitude. So if we draw a line through the center of our wave, that's not in the center, but that's just pretend it is. It's the amplitude is the distance between this line through the center of the wave and the peak, just like that. That is the amplitude. Now, one cycle of a transverse wave is measured from where the wave goes from, let's say, above this line to where it goes above, comes down, 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 and back up, and passes through this line again. So from there to there is called one cycle. A nice place that we see a transverse wave in real life is the vibration of a guitar string. As it gets plucked, it causes it to very quickly go back and forth like that. A couple of other things just to talk about is the period of a wave and the frequency of a wave. So the period of a wave is the time that it takes for a wave to complete one cycle. It's measured in seconds. So if I just draw one, that's one cycle of a wave there. So it's just simply the time it takes for this to get from here to here. That is essentially the period of a wave. The frequency of a wave is the amount of waves that pass through a certain point in a certain amount of time. Frequency is generally measured in a unit called hertz, or waves per second. The important thing about frequency, especially with longitude and the waves which make sound, is that the higher the frequency, the higher the pitch of the sound, or the lower the frequency, the lower the pitch.